success, you can have a failure. And it's the same, we still say probability distribution, still has to have your probabilities from 0 to 1, still has to sum up to 1. That's probability distribution. To be a binomial experiment, we have 4 conditions. One of them is the 2 possible outcomes, success or failure. And if you remember back from Algebra 2, you probably called it P and Q. P for success, Q for failure. This experiment is repeated for a fixed number of trials, that's your N. And each trial is independent of the other trials, so the probabilities are not going to change. The probability of success stays the same, it stays fixed, there's no, like it's going to change if you keep it with you or whatever, everything is independent. And your random variable X counts your number of successes. So you can have a 0 successes in this. You can have 0, if you do this 5 times, you can have 0, 1, 2, 3, 4, 5. If you remember this back in Algebra 2, we did this little thing, well maybe it's over here, let me see if it's here. We did this little thing here. We did one of these with the C thing, Bernoulli's. We do it a little bit different here. It's a little bit more fun. So again, just make sure that you know what symbols that we're using. And we're going to first determine if this is a binomial or not. So to be binomial, it has to hit those 4 conditions. So the first problem says a certain surgical procedure has an 85% chance of success. A doctor performs this procedure on 8 patients. This is your N. The random variable represents the number of successful surgeries. So we ask ourselves, what is N? 8. What is P? The probability of success. 85. What is Q? Failure. 1 minus, it's the complement. 1 minus 85. It could either be success or failure. And what do all your probabilities have to add up to? 1. So 2 choices, and the X can go from 0 to 8. Is this a binomial probability? Did it hit all 4 things? Yep, we have a fixed number of times. They're independent of each other. One surgery does not affect the next surgery. 85% chance it's either success or it's a failure. Okay, so that, yes, we say yes, that's binomial. Oops. Okay, a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. 5 red, 9 blue, 6 green. Add them up. 20 marbles altogether. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Would this be a binomial probability? Why? Very good. Without replacement is going to change your probability. They're not independent of the next one. And yeah, we still want a red or not a red. That's okay. We're going to do this a certain amount of times. But again, you're not replacing. So your probability is not going to stay fixed. So this guy is not a binomial. Okay? Let's take a look at another one. This is important that you know if it's a binomial or not. You take a multiple choice quiz that consists of 10 questions. Each question has 4 possible answers. And only one of them is correct. To complete the quiz, you randomly guess the answers to each question. The random variable represents the number of correct answers. Is this binomial? Yes? Let's see. What's N? Let's see if we can lay these out. What's N? How many questions are you answering? 10. What's the probability of success? Who said it? 0.25. How'd you get 0.25? 4 answers, 4 possibles, 1 is correct, right? So it's either going to be correct or not correct? Are those the two choices we have? P and Q? What's the probability that it's not correct? 0.75. And your variable represents, I could have 0 correct all the way up to 10 correct. So binomial. Even though you have 4 choices, there's only one correct. So you're either going to get a correct answer or an incorrect answer. So you have a binomial experiment. Now, way back in Algebra 2, you use this charming formula. And I hate when they do this part of it because it's so much easier than that. So say you did something for 5 trials, and our probability of success was, let's just make it easy, 0.2. Our probability of failure is 0.8. And x is going to go from 0 to 5. And what they probably said was, what is the probability that exactly 2 say yes? Let's just say they say yes. Okay? Back in Algebra 2, there was a nice little pattern to this. We did this 5 times. We wanted 2 correct. Okay? And you can absolutely do this again. You always measure your success before your failure. So your probability of success was 0.2. You wanted 2 of them. Your probability of failure is 1 minus this, 0.8. And out of 5, if 2 are successful, 5 minus 2 gives you 3. So this is what you did in Algebra 2 to get that. So that's a good review for anybody that needs to take that Regents too. This is how you figured these out. It's a nice little pattern. And you can put the rest of this in your calculator. You don't have to break it apart like they did. Now, the nice part about this is we have a calculator step for this. It's called, if you go to second VARs, we're going to look for the word binomial. Binomial probability distribution function. That's exactly what we're working on. We determined that this is a binomial probability distribution function. Probability distribution function because it has probability 0 to 1, and it has, they all add up to 1. Binomial because there's 2 choices. Now, instead of doing this, watch how nice this is. It says, how many trials do you have? I have 5. What's your probability of success? 0.2. What's your x value? Well, we're going to start at 0. What, we wanted 2? Let's put in, we said 2. Let's put in 2. And paste. Paste means it just set it up for you. If you're working on the 83 calculators, you have to put this in. Trials, comma, success, comma, x. So if you're working on the 83 calculators, you have to put it in that way. And that calculates your binomial probability. Now, if you wanted to do this a number of times, rather than have to change this guy, and this guy, all you have to do, all you have to do is this. Second enter, come over here, and say, give me the one for 0. There's my 0 one. Give me the one for 1. Give me the one for 2. Give me the one for 3. Give me the one for 5. It's a nice little calculator application rather than having to do your Bernoulli's one. And you can do either one you like. I like Bernoulli's. It has a nice little pattern to it. But when we make the tables, I find if you have to change 3 things, the chance of missing one of them is too much of a risk to do this. So this kind of works very nicely. Again, let me look this up. Second VARs. It's not a normal PDF. Normal PDF is different. That's when we're going to use that pretty soon. It's a binomial PDF. Now, binomial CDF means accumulate this. Like from 0 to 2, from 0 to 4, from 0 to 5. So we basically just use the PDF part because we want to fill out our table. We want to make the distribution function. And then we can answer all your probabilities off of that. Okay? It's not a bad calculator step. All right. So now, A rotor cuff surgery has a 90% chance of success. So if it has a 90% chance of success, what is its chance of failure? 10. So we know your P, and we know your Q. The surgery is performed on 3 patients. This is your N. Find the probability of the surgery being successful on exactly 2 patients. So again, lay out your parts. Sorry, that one. X could be from 0 success to 3 successes. Now you only want the 2. So if you use Bernoulli's, you say, I do this 3 times. I want 2 successes. Measure your success first. I want 2 of these. Therefore, you want 3 minus 2, 1 left over. If you use the binomial PDF, you have 3 trials, your chance of success, and how many times you want to be successful. They will both give you the same answer. Try both of them. I want you to be able to try both of them in your calculator. So take a minute and try both of them. On this. You're selecting 5 times. So what part is that? N. What is your probability of success? What are you measuring? Getting it close. 13 out of 52. Let's make it a lot easier. How many suits? 1 out of 4. You can use 13 out of 52. Or a 1 out of 4 it reduces to, right? Because isn't it 1 out of 4 suits? So either way you want to do this, 1 out of 4 or 13 out of 52. What's your 1 minus this? 3/4 or 39 out of 52? Okay. Either way you do this. What's your X? 3. You want exactly 3. Okay. Now you can use either one and leave it in a fraction. If you use this guy, you're doing this 5 times, you want 3 successes. Whether you put 1/4 or you put 13 over 52, it works the same way. Failure, I want the rest. Failure, oops, I want my rest. So it's going to work the same either way. Now, binomial PDF, same thing. You're going to do this 5 times. Your probability of success, leave it at a fraction. You always put your N, your P, your X. They go in alphabetical order. NPX. Yes. Nope. If you converted this, what was your decimal? Oh, that was your answer. That was your answer. Yeah, that's absolutely right. I thought you meant if you used the decimal here.
Oh, it's about 0.25.
Absolutely. 0.25 works perfectly fine. And we wanted 3 of these guys. So no matter what you did here, or if you put this guy in with 13 over 52, it would all give you the same answer. Okay? What's nice about the yellow calculators, well, the NE84s, if you have the software, it prompts you. If you don't have the software or you have the 83s, you just have to string it out. But look, your letters are in alphabetical order. NPX. Okay, I want 3 out of 5, and I want to just be successful. Think of it that way. Everybody's good with that? Okay? Okay. Now, what we usually do from this is we just make a table of all possibilities. Of course, we keep our N within reason. I'm not going to ask you to make a table that goes 50 times. We do something a little bit different when it comes to that. But if it's up to like 6 or 8 or 7, we can absolutely make a table for these guys. When we go to look for our probabilities, we'll pull our probabilities right off this table. And if you use the binomial PDF, all you have to do is second enter, change a 0 to a 1, change a 1 to a 2, change a 2 to a 3. That's it. So let's take a look at this guy. In a survey, U.S. adults were asked to identify what devices they use to access social media. The results are shown in the figure. So you kind of have to look at your book, and the results are shown on that little tablet that they're looking at. That's where your success is going to come from. 7 workers are randomly selected and asked whether they use a cell phone to access social media. So we care, did you use a cell phone or not? We don't care about what else they use. We just said cell phone or not. There's our 2 choices. Success, cell phone, not, failure. We want to construct a binomial distribution for the number of adults who said yes. So how many adults are we surveying? We randomly took how many workers? 7. If you look at your chart, go look at your chart. We want to know what is the probability that they use their cell phone. Read that little tablet. What's the probability that they use the cell phone? 0.46. That's our success. We don't care what else they used, but just it wasn't a cell phone. So what's 1 minus 0.46? By 4. Good. And our successes are going to be from 0 to 7. Is this a binomial probability? Yep, it meets all 4 conditions. A fixed number of trials, probability of success and failure, those are our 2 outcomes. The probability stays fixed, and we can measure x. So now all we need to do is make a table for this. So don't forget to count to 0, because you can have 0 that responded, nobody responded. Now, easiest way to do this is your binomial PDF. If you want to use your C, that's absolutely fine. Start with 0, then change it to 1, then change it to 2, then change it to 3. Go all the way up to 7. Go ahead. Complete the table for me. If you do your C, same thing. Start with 0. Probability of success, 0. Failure, 7. When you do this, you're going to have to change this, and this. Go to the 1. Then this becomes 1, 1, 6. 2, 2, 5. Just remember to change 3 places rather than just this. So give me your table. Go 3. Probability, you try to go 3 because it's better if we ever flip it to a percent that we have a little decimal place. So everybody got these numbers? What do all those probabilities add up to? 1. So this tells me this is a probability distribution function because it meets my 2 conditions. All my probabilities are between 0 and 1, and all my totals add up to 1. So I have a probability distribution function here. The binomial part of it says, oh, you're going to do this 7 times. Your probability is going to be 0.46. It's not going to change. You have a success and a failure, and they're independent of each other. So those are my 4 things that make this binomial. 2 things that I needed to know first to be a probability distribution, and then a binomial. Now, after you have this, usually they will say, what is the probability that exactly 2 said yes? Then you go to your graph, your chart, and there's your exactly 2. What is the probability that at least 4 said yes? What do I do to this one? At least 4. Good. From 4 up, add those together. Look how nice this is. I just take this and I add these together. Right? Because I have it all right in front of me now. What is the probability that at most 2 said yes? What would I do to my at most 2? 2 to where? To 0. Good. I add 2 to 0. Okay? So isn't this much, much easier using your binomial PDF? You loved it? Great. Great. I love the enthusiasm. Everybody get it? Okay, Michael, you want to yell me out your probabilities? Oh, okay. Raven, your probabilities?
0.295, 0.393, 0.225, 0.071, 0.014, 0.002, 9.865,
I'm sorry.
9.865.
Okay, but the 9.86 says what after it? E to the what?
Oh,
Negative 5?
Yeah.
Thank you. That means, because our probability could never be greater than 1, right?
Yeah.
That means I'm moving this decimal 5 positions. So I'm going to add 4 zeros in front of this. And look how small your numbers are getting. And the last one should be what?
2.60.
Again, you're going to move it 6 decimal places. You're going to give me 5 zeros in front of it. What should all these probabilities add up to? 1. If I graph this, where's the skew? To the right or to the left? To the... Where's the tail going to be? I got all my big numbers sitting right here. Just kind of visualize your bars. Here's my big bars. What's happening over here? Where's my skew? To the right. My skew is to the right. Okay? Now, there's also a little thing. I want to find it where it is. Hang on. Give me 1 second. I never remember where it is. I might have it on your notes. Maybe that's easier. Okay, yes. Look on your notes at the very bottom. The very bottom of the page. Binomial distributions can be skewed. We see the skew. If the probability of success, here's my probability of success, is greater than 0.5, greater than 50%, my skew is going to be to the left. In other words, my bigger bars would be here because my probabilities are better, right? For success, if it's greater than 0.5, it would go this way. If my probability is less than 0.5, such as this, we don't expect a lot of them to be successful, right? We just expect a few of them to have a better success rate. So my curve is skewed to the right. If my probability is exactly 0.5, I have a normal distribution. My curve is symmetric. Does it make sense where your heavier bars are? If I did one, and this says probability is, let's reverse this, 0.84, and my Q was 0.16, that means if I'm only looking for 0 to be successful, well, my rate is pretty good to be successful. So the fact that I had none be successful is probably very small, right? If my probability to be successful is 84%, and I did 7 of these, I asked 7 people. Is it possible that no one said yes out of 7 people? It's very small. Now, when I asked 5 or 6 people, these are where my bigger bars should come out, up here. So it kind of makes sense where your skew goes based on your probability. Does that make sense? Okay.